Welcome, curious minds, to another deep dive. Have you ever paused to consider how accurate those grand, influential energy projections really are? Do they reliably chart our course toward a sustainable future, or might some of them be, well, lagging behind the actual pace of change? Today, we're plunging into a truly illuminating analysis. It's titled, Paving the Way Towards a Sustainable Future, or Lagging Behind, an ex-post analysis of the International Energy Agency's World Energy Outlook. And this compelling study meticulously scrutinizes the projections from the International Energy Agency's flagship World Energy Outlook, which, since 1993 has been a critical compass, guiding global energy trends and often directly influencing national policies.
Indeed. And our mission, this deep dive, is to truly understand how well these IEA projections have measured up against real-world developments. We'll be particularly zeroing in on the explosive growth of key renewable technologies, the evolving role of nuclear power, the accelerating pace of electrification, and also this innovative emerging concept called the power-to-X economy. And we'll need to differentiate between the IEA's outlook scenarios, which often project current trends forward, and their more ambitious normative scenarios, which aim for specific sustainability goals.
Right, the ones aiming for things like net zero. And what this study uncovers is quite remarkable, isn't it? It suggests that while the IEA has shown commendable accuracy with overall energy demand, sort of at a macro level, their projections for specific technologies have painted a dramatically different and perhaps surprising picture. So what do the researchers discover when they compared these projections to reality?
Well, the analysis does confirm that at a broad macro level, the IEA has been largely on target. They've managed to be quite accurate in their projections for total primary energy demand and total final electricity demand. And that's even navigating significant global disruptions like the 2008 financial crisis and, more recently, the 2020 COVID-19 pandemic. That stability in overall demand projection is definitely notable.
That does sound like good news initially,
Yeah.
suggesting a steady hand on the tiller for the big picture, right?
Yeah.
But you emphasized macro level. So where did the details, those crucial individual technologies, start to tell a different story? What was the general trend once you kind of zoom in?
That's exactly where the significant deviations become clear. Historically, this study reveals a really consistent pattern. The IEA consistently overestimated the growth of fossil fuels and, interestingly, nuclear electricity generation. Conversely, they severely underestimated the growth of key renewable technologies like solar photovoltaics and wind power.
Severely underestimated.
Yes. And this trend wasn't just confined to one type of scenario. It was observed across both their more conservative outlook scenarios and their more ambitious, sustainability-focused normative ones.
Okay, that divergence is where things get really fascinating.
Yeah.
How much specifically were those promising renewable technologies underestimated? Let's maybe start with solar PV. It's just transformed the energy landscape so dramatically.
Solar photovoltaics, or PV, yes, it stands out as a prime example. This study highlights its truly remarkable growth. It notes a compound average growth rate, or CGR, of 34% just from 2010 to 2022.
34% CGR.
Exactly. And CGR, for listeners, is essentially the average annual growth rate over that specific period. Smooths out the bumps. And during that same time, the cost of solar modules just plummeted, dropped around 39% from 2006 to 2022 alone. The IEA itself, recognizing this meteoric rise, even went so far as to call solar PV the new king of global electricity markets at one point.
The new king. Yet, despite that declaration and the clear cost trends, this study found that their own projections didn't quite capture that regal status.
Precisely. The numbers are quite striking when you lay them out. For instance, none of the IEA's outlook or normative scenarios projecting out to 2020 had annual solar PV capacity installations above 57 gigawatts per year. That's 57 G-boy.
Okay, 57 GW a year projected for 2020.
Right. And just for context, a gigawatt is, a huge amount of power. Now, compare that IEA projection to the actual historical data. 241 GW were installed in 2022.
Wow.
0.456 GW in 2023, and an astonishing 593 GW are projected for 2024.
Goodness.
So you're looking at a difference of a factor of 4 to 10 between the IEA's past projections and what actually happened or is happening. It underscores a truly significant underestimation.
A staggering discrepancy for those near-term projections. Does this analysis offer any insight into whether this underestimation continues, especially in the IEA's longer-term outlooks, like those ambitious net zero emissions scenarios?
It absolutely does. The pattern seems to persist. Even in the IEA's most ambitious scenarios, like their net zero emissions or NZE scenarios, annual solar PV additions are projected to peak at around 657 GWh.
Okay, peak at 657 GWh per year.
Mm-hmm.
Still a lot.
But compare that to what leading international solar PV experts are now projecting. They're talking about annual installations of 2 to 3 terawatts per year. That's TWA, where 1 terawatt is 1,000 gigawatts by the 2030s.
2 to 3 terawatts a year.
Yes,
Yeah.
and potentially even up to 4 TWA by 2050. So the total installed solar PV capacity in the IEA's NZE scenarios reaches a maximum of 15.5 terawatt peak, or TWP, by 2050.
15.5 TWP total.
Compared to a 75 TW range expected by these independent experts. The difference is, well, it's immense.
So given this persistent, substantial underestimation, even in the scenarios designed for sustainability, what underlying reasons does this study suggest? Why this recurring pattern in the IEA's modeling? It almost sounds like there's some kind of, I don't know, invisible barrier or cap.
This study indeed suggests there might be something like an artificial cap influencing how renewables and power-to-X technologies are modeled within the IEA's framework.
An artificial cap. How would that work?
Well, this cap potentially results in a bias towards other energy sources like nuclear power, bioenergy, and perhaps even fossil fuels, coupled with carbon capture and sequestration. For example, the study mentions the Global Energy and Climate Model, the GEC model, which the IEA uses. It reportedly assigns additional costs to solar PV and wind power. These costs are meant to reflect perceived inflexibility or lower full load hours.
The variability issue.
Exactly. And simultaneously, it might give credits to technologies with higher full load hours, such as nuclear power. This kind of modeling choice can inherently limit the projected growth trajectory of variable renewables like solar and wind.
That's a really crucial point about the underlying modeling assumptions. They can really shape the outcome. Now, shifting gears from solar's underestimation, what about nuclear power? Did this analysis uncover a similar pattern of discrepancy there, or was it different?
Yes, it did find a pattern, but it was the inverse, actually. The IEA's World Energy Outlook, the WEO scenarios, have consistently overestimated the role of nuclear electricity in the global generation mix.
Overestimated, okay.
While nuclear generation did experience a period of linear growth earlier on, it largely stagnated between 2006 and 2020. The WEOs published between 2006 and 2016, for instance, overestimated the actual 2020 nuclear electricity generation by a considerable 14 to 39%.
14 to 39% higher than reality.
Correct, and even their normative scenarios, the ones aiming for higher sustainability, projected more nuclear growth than what actually materialized.
So we're seeing an overestimation here, not an underestimation like with solar. What factors, according to this study, contribute to this perceived over-optimism for nuclear power?
The study points to several critical factors stacking up against nuclear. Increasingly complex licensing processes, certainly. Growing safety concerns, especially post-Fukushima, have played a big role. And critically, escalating costs.
Costs, right. That's always a major discussion point with new nuclear.
Exactly. The costs for new nuclear power plants have consistently outpaced the initial estimates. They've actually demonstrated what the study calls a negative learning effect.
Negative learning. So the opposite of solar getting cheaper.
Precisely. Instead of getting cheaper with experience, new nuclear plants have tended to get more expensive. The report even cites Monte Carlo simulations, suggesting negative net present values for both third-generation nuclear plants and the newer small modular reactors, or SMRs.
Even SMRs. They're often touted as a potential solution to the cost issue.
Well, according to these simulations cited in the study, even SMRs face significant economic challenges. SMRs, for listeners, are those smaller, potentially factory-built reactors.
That's quite a contrast to the learning curve we just discussed with solar. So if nuclear power is looking like a more expensive, perhaps less flexible option, what implications does this study draw about its long-term role in a future truly decarbonized energy system, especially one focused on cost-effectiveness and flexibility?
Well, the analysis suggests that in an energy system that's going to be heavily reliant on flexibility and low-cost electricity, particularly one evolving towards what we're calling a power-to-X economy, expensive baseload generation from nuclear power might not be the most viable or cost-effective technology for deep climate change mitigation.
Right.
The need for agility and, frankly, economic efficiency in a future dominated by low-cost variable renewables might challenge nuclear's traditional role.
You've mentioned this intriguing concept of a power-to-X economy a couple of times now. Could you maybe unpack that a bit more for us? Explain what that truly entails, and then tell us how the IEA's projections align, or maybe don't align, with this vision for full defossilization?
Certainly. A power-to-X economy, in essence, refers to the widespread use of renewable electricity, often surplus renewable electricity, to produce other things. Primarily, it's used to produce hydrogen, often called e-hydrogen or green hydrogen, through electrolysis. But the X in power-to-X represents a whole range of other synthetic fuels and chemicals derived from that e-hydrogen and captured CO2 or nitrogen.
So using electricity to make fuels and chemicals.
Exactly. Things like synthetic methane, methanol, ammonia, or jet fuel. And these are then used to decarbonize sectors that are notoriously difficult to electrify directly. We often call these the hard-to-abate sectors.
Like heavy industry, long-haul transport.
Precisely. Long-distance shipping, aviation, heavy industry like steel making, and chemical production. It's really seen as a pivotal strategy for achieving complete defossilization across the whole economy.
That sounds like a really comprehensive approach, getting into those tricky sectors. So how well do the IEA's most recent, most ambitious scenarios, particularly the net zero emission scenarios, integrate and address the potential of this power-to-X future?
Well, what's fascinating here, and perhaps a bit puzzling, is that while the IEA's NZE scenarios do project significant direct electrification, they aim for about 49 to 52% of total final energy demand by 2050 coming from direct electricity use in areas like road transport, think EVs, and heating with heat pumps.
Which is substantial progress on electrification.
It is, but the integration of power-to-X solutions remains surprisingly limited in their same scenarios. For instance, looking at hydrogen production, while it does increase, it's still significantly reliant on fossil fuel-based hydrogen that uses carbon capture and sequestration. That's often called blue hydrogen.
Blue hydrogen, right,
Yeah.
made from gas, capture the CO2.
Correct. And that accounts for somewhere between 27 to 40% of total hydrogen production in their 2021 and 2022 NZE scenarios. So even in these pathways aiming for net zero, there's still a heavy reliance on fossil-derived hydrogen.
So even with these ambitious climate targets, the picture isn't one of full 100% electrification across all sectors or a really comprehensive power-to-X transformation driven purely by renewables. Why does this study suggest that's the case in the IEA models?
That's right. It's not a fully electrified or fully green powered-X-driven future in those specific IEA scenarios. This study highlights that, interestingly, in the IEA's NZE scenarios, biomass-based fuels often receive a proportionally higher share of final energy consumption compared to hydrogen and hydrogen-based fuels.
More biomass than hydrogen.
In some key areas, yes. To give you a concrete example from the study, in the 2022 NZ scenario, looking out to 2050, biomass is projected to account for 13.9% of the final energy mix. Meanwhile, hydrogen and its derivatives combined are only projected at 8.6%. This indicates, according to the study's authors, a significant, potentially unexploited potential for electricity-based solutions, particularly in industries like steel and chemicals. In those sectors, fossil feedstocks still constitute a substantial portion of the projected demand even in 2050 in the NZE scenario. Power-to-X could replace more of that.
And what are the knock-on effects? What are the implications of this somewhat limited power-to-X penetration in the models? How does it ripple through the IEA's other projections, especially for renewables?
This limitation, according to the analysis presented in this study, effectively creates another kind of artificial cap, this time on the projected growth of variable renewables, particularly solar PV and wind power.
It connects back.
It connects right back. Because to fully electrify those hard-to-abate sectors through power-to-X would demand a truly massive ramping up of variable renewable energy generation. You'd also need a huge deployment of electrolyzers to make the hydrogen, and then e-fuel synthesis units to make the X. The study strongly suggests that the IEA's projections for e-hydrogen, specifically, significantly underestimate its potential, and arguably its necessary role as a crucial intermediate step to fully defossilize global energy industry systems.
That makes perfect sense. If you don't fully account for the huge demand that power-to-X will create for cheap, abundant renewable electricity, then the projections for the renewable supply side will naturally appear capped or limited. It becomes a kind of circular logic. Okay, beyond solar, you mentioned wind power earlier as another significantly underestimated renewable. Could you just briefly touch on wind's trajectory? How did its actual growth compare to IEA projections?
Absolutely. It's a very similar story to solar PV, though perhaps starting a bit earlier. Wind power, despite its incredibly rapid growth, showing a 21.8% compound average growth rate just from 2000 to 2020, was also significantly underestimated in the IEA's outlook scenarios. In some cases, the study found the underestimation was by over 80%.
Wow, over 80% underestimation for wind, too. That's really substantial. Can you give us any quick numbers like you did for solar?
Sure. If we look back at, say, the IEA's 2010 World Energy Outlook, their main outlook scenario at the time projected only about 20 gigabu of annual wind installations globally by the year 2020.
20 GW a year projected for 2020.
Yet by 2020, the actual global annual additions were over 90 gigabu.
90, so more than 4 times higher.
Exactly. And that acceleration continued with over 117 gigabu installed in 2022 and another 118 gigabu estimated for 2023. So similar to solar, we see their long-term outlook scenarios for wind, even the ambitious ones, often peaking at figures that actual installations are already significantly surpassing today.
It really speaks to a consistent challenge in anticipating the speed and scale of deployment, doesn't it? And the impact of cost reductions.
It does. Both solar and wind have benefited immensely from technological advancements like larger, more efficient turbines for wind and those dramatic cost reductions. The scalability, both onshore and increasingly offshore for wind, has also surpassed many earlier expectations.
Right.
The sheer potential of untapped wind resources, combined with supportive policies in many regions, just allowed it to grow far faster and become more competitive than those earlier projections envisioned.
Okay, so solar and wind massively underestimated. What about other renewable technologies that aren't solar or wind? Did the study shed light on their projected roles according to the IEA?
It did touch on others. For those, the picture is a bit more varied. Hydropower, for example, is a very mature technology. It's generally projected for near linear growth, but with naturally limited potential going forward, as most of the best, most viable sites have already been developed.
Makes sense.
Concentrating solar thermal power, or CSP, and geothermal electricity. Well, the study notes they were actually initially overprojected in the 2010s by the IEA.
Oh, interesting. Overprojected.
Yes, but now they're generally seen, in the more recent projections, as having relatively limited roles compared to the sheer scale and cost effectiveness of solar PV and wind. Even nascent technologies like wave power are projected to have only a marginal contribution, even in those sustainability-focused scenarios. So the heavy lifting for decarbonization, this analysis strongly suggests, truly rests overwhelmingly with solar PV and wind power, coupled with that potential for power to X.
Okay, that provides a really clear picture of the different technologies.
So just to summarize the core findings from this analysis, this comprehensive ex-post analysis reveals a crucial, consistent pattern. While the IEA's World Energy Outlook has been quite accurate tracking macro energy demand trends, its projections have consistently and significantly underestimated the exponential growth of solar photovoltaics and wind power. Simultaneously, it has tended to overestimate the future contributions of fossil fuels and nuclear power. And this oversight, the study argues, extends to not fully recognizing or perhaps modeling the immense potential of deeper electrification combined with a robust power-to-X economy, even within scenarios specifically designed to achieve sustainable futures like net zero.
So what does this all truly mean for you, the listener, and maybe more broadly, for policymakers and investors worldwide? These projections, they aren't just academic numbers sitting on a shelf, are they? They are foundational. They actively shape global energy policy, they direct billions, probably trillions, in investment decisions, and they influence our collective path toward tackling climate change. And if these authoritative outlooks from leading institutions don't fully embrace or reflect the rapid, cost-effective transition being driven by renewables and potentially by power-to-X solutions, they could inadvertently create a kind of self-fulfilling prophecy, couldn't they?
Yeah.
Actually slowing down our critically important journey to climate neutrality.
That's certainly the concern raised by this analysis.
This study, it seems, strongly advocates for, well, a couple of key things. Firstly, greater transparency in the modeling assumptions being used. And secondly, crucially, a deeper exploration of scenarios that fully demonstrate the technical and economic feasibility of much higher variable renewable growth and more comprehensive power-to-X applications. It really leaves us with a powerful question to ponder, doesn't it? What if these influential institutions truly embrace the most ambitious, yet technically and economically feasible visions of a power-to-X economy? One powered by truly massive deployments of solar PV and wind, scaled up much faster than currently projected in even the ambitious scenarios. How quickly could we then truly defossilize our global energy industry systems? Something profound to think about as you navigate the complexities and also the immense potential of our shared energy future. This has been a deep dive into paving the way towards a sustainable future or lagging behind, an ex-post analysis of the International Energy Agency's World Energy Outlook. Until next time, keep digging for those insights.